Hello viewers, in the last program we have seen the verification of VI characteristic of UJT. In this program we are going to see one of a very important and interesting application of UJT, which is relaxation oscillator. With the help of this setup before you, we are going to see the relaxation oscillator using a UJT, and what we are going to use here is a CRO, which is a dual trace CRO, a power supply, and of course the main board. But before we take up the experimentation part, let me explain what is relaxation oscillator. You know that the UJT has 3 terminals, and the terminals are, what are the terminals? The emitter, base 1 and base 2. Now you also know that the emitter is spaced such that it is nearer to B2 with respect to B1. That means if I have the resistance between emitter and base 1, that should be greater than the resistance between emitter and base 2. But this is when the device is non-conducting, and what will be the position when it is conducting? Reverse, that is resistance between emitter and base 2 will be greater than resistance between emitter and base 1. This is for conducting state. Now let us see what happens if I energize the device. Suppose there is a resistance connected here, there is a resistance connected here. This will be of course RB1, which is connected across base 1, and this resistance which is connected across base 2 will be RB2 obviously. Suppose I connect a power supply between the 2 bases like that. So this power supply which is connected between base 2 and base 1 will be inter-base power supply, and I call it VBB. Now one thing is sure, that this B2 has to be positive. So this terminal will be positive and this will be negative. Okay, VBB is the inter-base supply connected between base 1 and base 2 such that B2 is positive with respect to B1. Now suppose I connect a resistance here. Resistance is to be connected here. Suppose like this, and also a capacitor, and I connect this terminal here like this. This is say a variable resistor R, and this is C capacitor. Now what will happen? If I have a constant voltage here, but I have a variable resistor here, I can change the value of the resistor, which is nothing but an RC circuit connected across the VBB. So what will happen if I change the value of the resistor? The voltage across this capacitor will change. In other words, I can say the rate of charging of the capacitor will change, and that will depend on the value of the resistor. If I have a more value of resistor, it will charge quickly. If I have lesser value, it will charge slowly. Okay. Now what happens is, here a voltage say VE will be developed, and that will depend on the value of R. I could have a variable capacitor also, but it is easy to have a variable resistor. Now what will happen to this device, which is nothing but UJT, if I have an arrangement like this? I keep on changing the value of resistance, so VE will be developed across this UJT depending on the value of R. Now one position will come when VE will be such that the PN diode of the UJT will be forward biased. Once it is forward biased, the UJT will start conducting, and you all know that once it starts conducting, it has a negative resistance characteristic. Negative resistance. That means the negative resistance means the voltage will droop and the current will increase, and the conduction is towards B1. So we can have an output which will be available across RB1. Here we will have the output, say VO is the output, so it will be available. Now what happens, what will be the shape of the wave, what you get as the output? You know that this capacitor will first charge, and when it charges, up to what voltage will it go? It will go to the voltage of Vp, that is peak point voltage of this UJT. And you remember that in case of 2N2646 or 2N2647, we had Vp, that is peak point voltage, approximately 8 volt, and valley voltage Vb approximately 1.5 volt. This is peak point voltage, and this is valley voltage. Right? Now let us see what will be the shape of charging, discharging, and what will you get as output across B1. If I draw it like this, okay, so this is V and this is I, that is current. We have, say, this is VV, which is valley voltage, and say this is valley voltage, and say this is the peak point voltage, which is Vp. What will happen to the capacitor? The capacitor will charge up to this voltage, and then it will discharge up to this voltage. Again it will charge, discharge, again it will charge, discharge, and so on. Now let us see what will be the output. Suppose I draw the output here, then project them. If I project it like this, the output will be somewhat like this. And this is the output, say VO, which you are getting across B1. Now what are these? These are nothing but pulses, okay, and that is why we call them as output pulses. And since there are so many pulses, we can say it is a train of pulses. Train of pulses. And here two things are very important. One is the amplitude of the pulse, amplitude, and the other thing is its width, pulse width, Okay? So you have one pulse, second pulse, third pulse and so on. It is a continuous process. That means we have a train of pulses as output across B1. Now I have said that this amplitude and width of the pulse are very important. Why? Because we want to use these pulses for triggering thyristors such as SCR or TRAC, etc. And in SCR you remember that one current which is known as Ig minimum is very important. Unless you give Ig minimum, the device will not conduct. This current has to be given at the gate of the SCR. Similarly, there is turn on time T on, that is also has a specific value. If you do not give that turn on time, that means if you do not hold the current till this T on, the device will not conduct. Now here, since we are using these pulses as triggering pulses, we would say that the amplitude of the pulse must match with the Ig minimum of the SCR and the width of the pulse must also match with the turn on time. If it is the width is lesser than turn on time, the device will not conduct. If the amplitude of the pulse is less than Ig minimum, it will also not conduct. So that is very important. Now since we are using these pulses as triggering pulses, we say that UJT is a triggering agent. And since these pulses are found out, they are developed with the help of relaxation oscillator, we say that the relaxation oscillator is a triggering device. Now we can also control the pulses. We can improve its amplitude or width, we can improve it, increase it, or you can reduce it also with the help of this RC circuit. If you change the value of RC, what is there? You know that there is a time which is known as RC time constant. It is given by 0.69 RC. Okay, 0.69 RC. If I change the value of R or C, I can change the time constant. So here what we are doing is we have taken a constant value capacitor and a variable resistor. We could have also taken a variable capacitor and a constant value resistor, but it is always easy to have a constant value resistor and a variable resistor and a constant value capacitor. Now since we can change the pulse width, what we are doing is we can increase or reduce this time which is between pulse 1 and pulse 2 or pulse 2 and pulse 3. Now one thing is very important, why we call it relaxation oscillator. You are seeing that between pulse 1 and pulse 2 or between pulse 2 and pulse 3 and so on, this time or this time the device is relaxing. That is why we call it relaxation oscillator. So relaxation oscillator is a very important device where we are going to use the relaxation pulses for triggering thyristors such as SCR, TRAC, etc. and we can also control it. So relaxation oscillator is a control device. Now this is the thing, the relaxation oscillator, the output pulses, the input charging and discharging. Of course this is charging of capacitor, this is the charging, and this is the discharging. Okay, discharging. So this thing we are going to verify with the help of the setup what we have before you. Okay, now let me explain the experimentation part. This is the main board, and in this board we are using this as the UJT, and you find that 2N2646 has been used for making this relaxation oscillator. Here you find that this is the potentiometer. Okay, the potentiometer is being used here as a variable resistor and the value of the potentiometer is 100K. Now across the UJT we have to give VBB. So here you see the 10 volt is being used as VBB. This is the positive terminal, this is the negative terminal, and this 10 volt will be taken from this power supply. Now you find that there are 3 resistors, one here, and one here. The resistor 62 ohm half watt resistor is connected across B1. So this will act as RB1. 680 ohm half watt, this is another resistor, this will be connected across B2, so this will act as RB2. Now there is another resistor here which is 1K half watt, this is being used in series with this potentiometer. As a thumb rule we have used it because whenever you are using a resistor or a variable resistor rather, then you must have one resistor in series with it. Now you have 3 capacitors here. This is 0.47 microfarad value, this is of 0.22 microfarad value, and this is of 0.1 microfarad value. This has been purposely done to make the experimentation more interesting. This is the common point, so I can connect one terminal here and one here or here or here. By that we can connect either this capacitor in circuit or this capacitor or this capacitor. So we can have different wave shapes, right. Now here you are finding that a switch is being used here. This switch is for energizing the circuit, and rest you are also finding 2 terminals here. This is the positive terminal, the red one, the black one, the negative one, and here output is to be taken out. This output wave shape will be seen on the screen of the CRO.
Action.
Let me now connect and perform the experiment for you. I would like to use my specs first. Okay, so this is 10 volt supply, so I will connect the positive here, and the negative will come here. This is 10 volt VBB, it has been connected. Let me connect the output over here. Output is connected on the CRO, and now I will switch on. Suppose the CRO is switched on, power supply is switched on, and let me fix 10 volts here. 10 volts have been fixed, put on, and of course now you see I am going to use first 0.1 microfarad capacitor. So I connect it here. So 0.1 microfarad capacitor is connected in the circuit, and of course potentiometer 100K is now being used as a fixed resistance here. So let me check up the output. Connect the probe across this capacitor, which is 0.1 microfarad, and you see here is the output coming. Okay, the output, this is the charging and discharging of the capacitor, and below second trace you are seeing the output pulses across this capacitor, which is 0.1 microfarad now. Now I am not going to change the potentiometer, but I am going to vary the capacitor because I have a provision here. So I will place it across the second capacitor now. Let me place it across this 0.22 microfarad now. And I will connect this capacitor now. You see it is different, the shape has changed because the charging and discharging rate has changed. So this is for the 0.22 microfarad. Now let me change to the third capacitor, which is 0.47 microfarad. This is the 0.47 microfarad capacitor, and I will connect it here. It has further changed. You see the charging, discharging, and the pulse strength further has changed. Now let me change the potentiometer. Okay, with this capacitor only. First let me change it. You see again it is changing. What is changing is the relaxation time. The relaxation time has changed. Okay, okay. I can change it to this place also, that is this 0.22 microfarad capacitor. So here and here also I can change with the potentiometer. You see the relaxation time has increased further. I can also change it to the first capacitor, that is 0.1 microfarad. Let me connect it here. So this will be connected here, and again I can now change it. Here. So with the help of potentiometer also I can change for a particular value of capacitor. If I make that constant and change this, this pattern is changing, as well as if I make this potentiometer as a constant resistor and change the value of the capacitor, then also it is changing. So friends, what we have verified here? We have verified that with the help of either variable resistor or variable capacitor, we can change the relaxation time, and hence the pulses will be obtained either earlier or later. So the firing of SCR or TRIAC, whatever it is where this pulse is being given, that will change, so the firing angle will change. So friends, we have verified the use of UJT as a relaxation oscillator in this program. In the next programs, we are going to discuss the applications of thyristors. Thank you.